Okay. Hi everyone. My name is Ahmad Zamirul bin Zainuddin. My number matric is 208129.
Hello everyone, my name is Sujana Samir Cynthia and my matric number is 205056.
Hello everybody, my name is Renzong Xiang. Matric number is 204887.
Hello, my name is Zhang Zixuan. My mixture number is 208746.
Alright. Today we would like to present our topic, which is recurrence relations. So first of all, we will go to the arrangement and selection without repeats. First of all, we need to know what is the arrangement in recurrence relation. As we all know, arrangement is known as a permutation. Permutation is an arrangement of some elements in which order matters. In other words, a permutation is an ordered combination of elements. So this is the derived equation. Before we have derived, and second is the combination. Combination is the selection of some given elements in which order does not matter, which means we have to select what of kind of element that we need to make it of it without any orders. All right. So this is an example arrangement without repeat. So we just use the formula and then we have to determine what is the number of an element and what the number of element that we need to be arranged. So, example, the word police has 6 letters. How many permutation without repeats are there if you choose 6 out of 6 letters? So we have just to input the formulas and we have got 720 ways to arrange the police without repetition. So next is selection without repeat. For example, there are 6 men and 5 women in a room. In how many ways we can choose 3 men and 2 women from the room? So in this case, we have 2 different elements, so we need to multiply it by selecting one of the element. So we need to calculate the man and also the woman. After that, we will multiply by 2 different element and then we get the final answer, which is 200 ways. So this is the formulas for selection for combination without repeat.
Next point is Fibonacci relation and application. Uh, First of all, we have to know what is Fibonacci relation. The Fibonacci relation is one of the most famous formulas in mathematics. Fibonacci numbers are used to create technical indicators using a mathematical sequence developed by the Italian mathematicians commonly referred to as Fibonacci in the 13th century. The sequence of numbers starting this with 0 and 1 and is created by the addition previous two numbers. Like if we see that the Fibonacci numbers commonly denoted by Fn from a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones starting from 0 and 1. We see that there is F0 is equal to 0 and F1 is equal to 1, and the rule is there Fn does it there is Fn is equal to Fn minus 1 is plus Fn minus 2 for the n greater than 1. If there is n greater than 1, we can use these formulas. Next, the Fibonacci sequence. By following these rules, we can found the sequence like 0, 1, 1, 2, 3, 5, 8, 30, 21, 34, 5, 55, 89, 1, 4, 4, and so on. Looking at that, now you can see that each number in the sequence is the addition or sum of the two previous numbers. For example, we see that 34 is the addition of 21 and 13. 144 is the addition of 89 and 55. But there is some problem that in some older books, the value for F0 is equal to 0 is omitted, so that the sequence start with F1 is equal to F2 is equal to 1. And thus the recurrence go from the valid for n greater than 2. Thus the sequence start from f2, like f1 is plus f0 is equal to 1 plus 0 is equal to 1. Thus this sequence is start from 1 and it's go on from the last point like fn. Next, there is some example. Let the sequence start same recurrence relation. Like let a1, a2, and a3, and there is b1, b2, and b3, and there is two initial conditions and two recurrence relations like ak is equal to 3ak minus 1 and bk is equal to 3bk minus 1, two recurrence relations, and the two initial relations is a1 is equal to 2 and b1 is equal to 1. Thus we can found that a2, a3, and a4, like if we can use the initial condition k is equal to a1, then the value of a is 2, then we can multiply this 2 and like 3 into 2 is equal to 6. Thus we can found the a3, a4's value, and also like this we can found b2, b3, and b4. We can also we can also describe this Fibonacci by the shallow diagonals in Pascal's triangle. Thus the formulas provide like fn is equal to n minus 1 by 2 summation of n minus k minus 1 by k, and the initial value is start from now is equal to k is equal to 0. Like the number is an order sum is called compositions. There are fn and plus f1 ways to do this. Like for example, if n is equal to 5, then f1 plus 1 is equal to f6 is equal to 8 counts the 8 compositors summation to 5. Thus, if we can see that from the trigonal Pascal's triangle, 5 is equal to 1 plus 1, 1 plus 1, and 1. And then with 2 summation of last one is equal to 2, then 1 plus 1 is plus 2. Thus, we can found the relation between the last one is equal to 1 plus 2 plus 2. Like these Fibonacci numbers can found in different ways among in the set of binary strings or equivalent among the subset of a given set. Next, we can also found these Fibonacci relations in the nature. Like we can also not only we can apply this in computers as search of algorithm. We can also use this in nature, like the stems of leaves, the branching of trees following or the architecture, and unicorn fern breaks are arranged also by this Fibonacci sequence. Like the most important application of this sequence is the rabbit of Fibonacci and the famous sequence that is called the Leonardo Fibonacci, who stumbled across it in the 20th century. We can see that if there is if we can see that the Fibonacci starts with a pair of fictional and scientifically unbelievable baby breed for rabbit, like a boy baby rabbit and a baby girl rabbit. Uh, if we basically describe the generation of this, as we can found that the fully grown after 1 month and did what rabbit do the best. The next month, two babies rabbit were born. The next month, their babies were fully grown, and the first pair had two baby pairs, like girl and boys. Ignoring problems of the breeding, the next month, the two adult pairs each have a pair of baby rabbits, and the rabbits from last month matured. In this, Fibonacci asked how many rabbits a single pair can proceed after a year with this highly unbelievable breeding process in this sequence. Next, we found we can describe it by the Fibonacci's number, like writing an for the number of adult pair in the nth month and rn for the total number of pair is nth month. This given an is equal to rn minus 1. And the next we can also found the same relations, right? Bn is equal to an minus 1 is equal to rn minus 2. Thus the total number of pair rabbits in a particular month is sum total, and total pairs of rabbits in the previous 2 months, like it was become to two the summations of an plus bn, and it began to rn minus 1 plus rn minus 2, the whole number of the rabbits. Starting with one pair, the sequence we generate is exactly the sequence at the start of that article, and from that we can see that after 12 months there will be the 144 pairs of rabbit we can found there. So it is an amazing breed pair of this sequence, and it is also the famous sequence.
Okay.
And there is also the importance of Fibonacci sequence. The Fibonacci sequence is used in many applications, not only in computers, but also we can found the example in our nature, and also we can found many nature and naturally to in case of branching in trees. So I think that's all for me. I will pass this discussion to my friend.
Okay. You can close your this, and I will share my screen. Okay. You can stop here. Then I share my screen.
Okay, you can present your own now.
Okay. Now, can you see my slide?
Yes.
Yes.
Okay. Today I will introduce you the Tower of Haniel Powder. Here is the background. In the 19th century, the French mathematician Lucas invented a powder consisting of 3 packs on a board with discs of different sizes. Initially, all of the discs are on the first pack in order of the size, with the largest on the bottom. Now we need to obey these rules. We are allowed to move the discs one at a time from one pack to another pack, as long as a larger disc is never placed on a small. Our goal is simple: use allowable moves, end up with all the discs on the second pack in order of size with largest on the bottom, which means we need to move the small to large discs on the tower A from tower C via the help of tower B. Let's see the next. Here we set each in to note that the number moves need to slow the tower of Haniel powder with in discs. So means each in equal the steps we need to execute the time, and in means how many discs there are. Set up a recurrence relation for the sequence each in, beginning with in discs on pack 1. Transfer the top in minus 1 discs following the rules of the powder to the pack C, which is the third pack, using H in minus 1 moves. Hence, we got this formula. We will talk about it later. Here we got an example. If we have 3 discs to move, how many times we need to move at least? Here, I will show you this. Can you see? Can you see it?
Yes, I can see.
Okay.
Yes, I can see it.
Good. We can use this as a model. Here are three disks, so you just need to follow this process. You see, congratulations, at least you need to move 7 steps. So let's back to the slide. Follow this formula. Hn equal to Hn minus 1 plus 1, and pass the process. The final output is 2 power n minus 1. And in this case, we have 3 disks, so h3 equal 2 power 3 minus 1 equals 7. Besides, we can use a short Java program to confirm it. Let's see it. Can you see this? My eclipse.
Yes, I can see.
Okay, good. Now we enter the number of disks. First we enter 3. So the output here, at least we need to move 7 times from pack A to pack C. And here are the details of process, how to move. It's same to this. Actually, they are same, but this is a model, just for understanding more easier. So let's back to this. If we have 4, also can run this program. You see, if we have 4 disks, at least we need to move 15 times from pack A to pack C. Here are the details of process. So I think that's all of the solution. About any questions about any tower? Okay, I will stop to share my screen.
Okay.
Okay. Herman, can you share screen again?
All right.
Okay. Yes.
Okay.
Okay. This map plots money growing in a saving account, compound interest. Einstein said compound interest is wonder of the world. The greatest power in the world is not the academic bone, but compound interest. The calculation of compound interest is to calculate the principal and the interest generated together. That is, the profit is variable. The characteristic of compound interest calculation is that the principal and interest of the previous period are taken as the principal of the next period, and the amount of the principal of each period is different when calculating. Next page. I will show 3 examples. First one, in stock investment, compound interest is powerful. Warren Buffett, the god of stocks, say he bets the market by compounding at an average of 30% a year and becomes a world-famous master of value investing. Assuming his initial investment is $10,000 and his annual investment income compounds at 30 centimeter, 30%. How much will his total assets be in his account at the end of 30 years? Solution is less PN is the total amount of assets in a few years, since the total assets in the amount after n years is equal to the assets in the amount for n minus 1 years plus the return of investment in the nth year. It's easy to know that the sequence PN satisfied the following recurrence relation. We can know P30 equal 1.3. 30 is equal multiply 10,000, we can get the answer. Next page. Next page. I can't see. It's the second question. Question is it know that the interest rate of return of an investment is R, and in this investment, C0 equal 3,000, C1 equal 1,000, R2 equal 2,000, and R3 equal 4,000. Calculation of R. Solution is let U equal 1 divided of 1 plus r, then p r equals 0. Put in the date and so forth, we can get the answer. Next page. And next page again. I have saved this page. The following investment methods are known. RMB is 7,000 at present, RMB 1,000 at the end of the second year. The return is RMB 4,000 at the end of the first year and RMB 5,500 at the end of the third year. Calculation is P 0.09 and P 0.1. Solution is not present, the value Pi is. We can see the answer after this. I think after my talking, you can know more about compound interest. That's all.
Okay, so last but not least, this is other application of recurrence relation, which is arithmetic and geometric progression and harmonic numbers. So first of all, arithmetic and geometric progression have the same of purpose that they use both using sequence involving a n in terms of one or more of the previous terms of the sequence, namely a0, a0, a1, until an minus 1 for all integers n with n more than n initial where n initial is non-negative integer. Both sequences call a solution of a recurrence relation if its terms satisfy the recurrence relation. And last, they need initial condition, which means the first term that precedes where the recurrence relation takes effect. For example, for the first is an equals to an minus 1 plus d for arithmetic and an equals to an minus 1 times r for geometry. Lastly, the harmonic number. The harmonic number are the partial sum of the harmonic series. The n terms harmonic number is the sum of the reciprocal of each positive integer up to n. It can also be expressed with the recurrence relation. For example, this is the equation that have been simplified by using a recurrence relation, which is harmonic n equals to hn minus 1 plus 1 over n. So this is the example. So we need to prove that these are the truths that the equation are similar to this equation, which means yes. So we have to solve it regularly. So negative 172x will be plus to 1729 in here. So the total up is positive 1. And then we divided all the equation by 1700 to 1729. So we have got the final answer is here. So we can see that this is the hn plus 1, hn minus 1 plus 1 over 1729 equals to h1729. So that's all from us. Thank you.
Okay, we can stop the recording.